Next is comparator. Comparator is to compare a given two values, either they are less than, greater than, or equal. And of course, sometimes we also want to check whether they are less than or equal to, or greater than or equal to. So this is the block diagram. This is how it looks like. The two input A and B are the signal that we want to compare. And if A is less than B, this output signal will be raised to logic 1. They are the two input, they are the two output, equal and greater than will be low. If A and B are the same or equal, then of course the EQ or equal to signal will be set to high. Less than LT and greater than GT will be set to low. And of course, also when A is greater than B, then the greater than line will be raised to equal to logic 1. The two inputs, the input A and B, can be multi-bits, and normally they are multi-bits. But the three output, LT, EQ, and GT, can only be single bit. That is the behavior of comparator. And another unique behavior of comparator is that out of these three output, LT, EQ, and GT, there will be exactly one, not more, not less, of them will be set logic 1 corresponding to the condition at the input. For example, if A less than B, then only LT will be 1, the other two will be 0. If A equal to B, only EQ will be 1, the rest will be 0. And if A is greater than B, only GT is 1, LT and EQ will be 0. Then sometimes we want to draw the block diagram for greater than or equal to. How do we draw it? We can take the obvious choice, since the statement says greater than or equal to. We may want to just combine the equal to output and greater than output together using an OR gate, so we get the GE, greater than or equal to. But this one is more preferred because this one will require only an additional 2 transistor to create the inverter, but this one will require an extra 4 gates, an extra 4 transistor to generate the combination of the two conditions. So how this one works? The logic is that because we want the output of greater than or equal to, so it is not less than. So the output, so the only output that was not touched in this diagram is being inverted. So the original two input from here stay as they are, but the less than input will be inverted. So this one becomes GE from LT. So you can expect the same thing for less than or equal to. Like this, the easy or less optimized solution or straightforward solution is by combining the less than and equal to output with an OR gate, we get less than or equal to. But a preferred solution is to put an inverter at the output of greater than. So we get less than this way. And again, this is preferred because it requires only an extra 2 transistor, while this one require 4 transistor. Then how do we write the code for them? If we want it to be in pure wire or pure combinational, the preferred way to write it is using conditional operators like this. For less than, in the condition part of the conditional operator, we put the condition less than, and if it is true, the value in between the question mark and the colon will be taken to the wire that we are connecting to. So let's say it's true that A is less than B, then a 1 will be given to LT. Otherwise, if this is false, it is given a 0. Similar goes to EQ and GT. For EQ, when A equal to B, we give a 1 to it, otherwise it's 0. For GT, when A is greater than B, we give a 1 to it, otherwise 0. And for GE and LE, for greater than or equal to, instead of putting greater than or equal to here, we can also put only less than, like this one, but we reverse the output. Instead of 1, 0 like this, it is 0, 1, similar to LE. We take greater than instead of less than, but we reverse the output. This one and this one. But of course, a more straightforward way is to actually use the greater than or equal to operation, like this. So if you use this operator, you compare it like this, then this one switch back to the original sequence or original condition. This has to be 1, this has to be 0. And for LE, of course, if you use the actual less than or equal to operator, you also need to switch the output. And if you use always block instead of assigning to wires, you can use if else like this. So it is a lot easier because we can see the operation clearly. If A is less than B, then the LT output will be given a 1, the rest given zeros. If A is greater than B, GT or greater than will be given a 1, the rest will be 0. And we don't have to check for A equal to B because we can just use else to say that this has to be the equal condition. So the EQ is given 1, GT and LT is given are given 0. So similar to the GE and LE in case of wire assignment just now, if you put A less than or equal to B like this, you have to change this one also. You need to add one more you have to add one more output to reflect LE. And if you put greater than or equal to operator in this case, you need to add one more or two more if you want both output LE and GE to reflect the condition that you are testing.